Okay, this is part 4 of kinetic energy and angular momentum. So we're going to do rotational kinetic energy and angular momentum in this. So rotational kinetic energy is compared to translational kinetic energy. We learned that kinetic energy is 1/2 mv squared. Rotational kinetic energy comes out to 1/2 I omega squared. We're not going to formulate that. We're just going to use that formula. We still measure the kinetic energy in joules, and so we're going to we will be using the kinetic energy translational also. So this is the energy of like an object sliding or moving, and the rotational, of course, is how much it's moving in a circle. So we're going to do an example to learn this. What is the rotational kinetic energy of a 35 kilogram solid concrete wheel? So imagine that you have this wheel, the diameter of 66 centimeters, that's more than half a meter, that is moving at 5 radians per second. Keep in mind that one complete circle is 2 pi, which is about 6.28. So it's going less than a full circle in 1 second, so 5 radians per second. Okay, so in order to get the rotational kinetic energy, we need 1/2 I omega squared. So we need to know what the what I is, and this is a solid concrete wheel, so I is 1/2 mr squared. You can look back on your notes and see a solid disk is 1/2 mr squared. The mass is given at 35 kilograms. The radius is we have to half the diameter, so it's 33 centimeters, and then switch it to meters as we normally do. And then 5 radians per second is the angular velocity. So to calculate this, we need 1/2 of I omega squared. So it's going to look a little weird, because if it's 1/2 I omega squared and I is 1/2 mr squared, it actually comes out to 1/2 of 1/2 mr squared, and then times omega squared. So be careful with that, because the first 1/2 is part of the formula for rotational kinetic energy, and the other half, it comes from the rotational inertia. Okay, so we put the numbers in. So we get 1/2, and 1/2 is 1/4. The mass is 35 kilograms. R is 0.33. We're going to square that. Be careful on that. Omega, which is 5, we're going to square that also. So you can calculate that, and you get 23.8 joules. Okay, well, the second part of this is, what is the total kinetic energy? Well, the total kinetic energy, or the sum of all kinetic energies, is the translational kinetic energy plus the rotational kinetic energy. So I just subscripted T and R. The kinetic energy rotational we just calculated is 23.8. Now, how do we do the kinetic energy translational? Well, of course, we use this formula. So that's going to be 1/2 mv squared. And if you remember from rotational kinematics, V is omega R. So we're going to take 1/2 m omega squared r squared. Almost looks like that, except this looks like it's going to be half of that. So we put the values in. 1/2 35, 0.33 times 5 squared. Be sure you use enough parentheses, or square them individually, like you learned in algebra. That calculates to 47.6. So the sum of all the forces, or the total kinetic energy, is 47.6 plus 23.8 for a grand total of about 71 joules. Okay, so that's rotational kinetic energy. Now, angular momentum, we're going to address the same way. When we learned linear momentum, remember that was P equals mv. Well, angular momentum is labeled with an L, and that equals I omega. And those units come out differently than linear momentum. Remember, the units were kilogram meters per second. Well, this is kilogram meters squared per second. And the reason is because there are 2 dimensions going on there on these objects that go around. Okay, so let's take a look at an example. What is the angular momentum of a 3 kilogram bicycle wheel with a diameter of 66 centimeters that is moving at 5 radians per second? So we haven't really changed the numbers much. So we have this bicycle wheel now. So in order to get the angular momentum, we of course need to list the I. And now this is a wheel, so we're gonna use the first one, the thin hoop rotational inertia, so mr squared, and r is 0.33. Remember, we have to half the diameter and then move the decimal over twice, and then omega is 5 radians per second. So we can simply put L equals I omega in, put the mr squared omega, and then put the numbers in 3 and 0.33 squared and 5. So this calculation comes out pretty simple, 1.6 kilogram meter squared per second, because kilograms meter squared per second. Remember, the radian is not a unit, it's a label to indicate what type of angle it comes from. So just like this conservation of energy and conservation of momentum in a linear sense, there's also conservation of angular momentum. And the total angular momentum of a rotating object remains constant if the net torque acting on it is 0. So this translates into mathematics as the angular momentum, I omega, is constant. So that means it does not change. If the mass distribution changes, that's I, then the angular velocity change. So if we have the beginning I omega equal to the ending I omega, and something changes, then the other one has to change also. If I decreases rather, then omega increases, and vice versa. Let's take a look at an example of that. You can see that the skater is turning around. She's got extended all the way out, and then she brings her mass inside and she turns around faster. So she's not putting any more energy into the spinning. She's simply going faster because of the moment of inertia, or the mass distribution changes. Let's look at another one. This one's a little bit interesting. This one's got some narration going along with it, so listen up.
Moment of inertia. Moment of inertia can affect angular velocity. I will spin over there, and my moment of inertia will be very high because I will be quite far from the axis around which I will be rotating. As I will pull myself closer to the axis, my moment of inertia will decrease, therefore I will spin faster. And this is the practical explanation. You will see that.
Now, I wish we had one of these at the school that we could play around with, of course. So here his moment of inertia is large because his mass is distributed way out from the axis of the axis of rotation.
Very slowly. But as I will pull myself closer to the axis, I will spin faster. Look.
So now he pulled himself in. Now there's no way he's applying any other force from the outside because everything he has is rotating. So when his moment of inertia becomes smaller, then it compensates by spinning faster.
That was the practical example, and my head is spinning.
Okay, so let's try a problem like this. So we have a skater, like from the video, mass of 35 kilograms, arm length of 1.75 meters, is rotating at 0.75 revolutions per second. When her moment of inertia is 1/12 ml squared. So this is like a bar that's that's rotating. You can look back in your notes on all the moment of inertias. We're going to calculate our angular momentum. So we do that by angular momentum is equal L is the letter L, and that equals I omega. So I is the 1/12 mL squared, but omega, which we have to calculate into radians per second. We do that by taking the revolutions per second. One revolution is 2 pi, so we simply take 0.75 times 2 pi, and that comes out to 4.75 radians per second. So we're going to take that value as omega, and we're going to put in 1/12 mL squared. And so we have 1/12 of the mass 35 and 1.75, which is L squared, times 4.71. We calculate that, and that comes up to 42.1 kilogram meter squared per second. So that's her angular momentum. Okay, so she's spinning around at this, so that means she's going pretty slow, 3/4 of a way around in a second. So imagine a circle and going 3/4 of that in a second. When she's stretched out and her arms are out almost 2 meters. Not quite 2 meters, but whatever. Okay, so now if she changes her moment of inertia to I equals 1/2 mr squared, so that's the moment of inertia for a cylinder. So she's now just bringing her arms in, and her radius is 0.25 meters. We're going to calculate our angular velocity in revolutions per second. Okay, so we start out with the conservation of angular momentum, which is Li equals Lf. We can simply put our numbers in. So 42.1 is what we calculated before. 1/2 of 35, which is 35 is the mass, and then r squared is now it's 0.25 r squared. And so remember that we're getting I omega, so that's the I part. I is that, and then omega is what we're calculating. Okay, so we're going to take and do this calculation. We're going to multiply both sides by 2, and then divide by 35 and divide by 0.25 squared. When we do this calculation, it comes out to 38.5 radians per second. We could compare that to the 4.7 radians per second, so you can see how much faster that is. But it asks us, we want revolutions per second, so we're going to divide now by 2 pi, and that comes out to 6 revolutions per second. Remember, it was 3/4 of a revolution per second. Now it's 6 revolutions per second, which is quite fast. So that's why you see those skaters, they're turning, and they almost look like a blur. Okay, we got one more example. So we have a ball that's 1.2 kilograms. Okay, so it's a heavy ball on a string and rotates with an angular speed of 33.5 radians per second when the string is 60 centimeters. What's the angular speed of the ball if the string is shortened to 20 centimeters per second? So this is the direct calculation of the conservation of angular momentum, where the initial angular momentum equals the final. So we can take the I omega at the beginning is equal to the I omega at the end. At the beginning, the I was given as a ball on a string, so that is mr squared at the beginning. Well, the I is the same as mr squared, except the masses are the same, but the radiuses are going to change. So we could take the 1.2 kilograms times 60 centimeters squared. That would be the mr squared times the initial angular velocity, 3.5 radians per second. And that equals mr squared, which is 1.2 kilograms, 20 centimeters squared. And notice that I cross out the mass from both sides. You could do that because they don't change. So we could essentially do that in the formula up here. Just take out the masses from both sides. So to calculate this, we're going to take 60 squared times 3.5 and divide that by 20 squared. And that comes out to simply 31.5 radians per second. From 3.5 radians per second to 35 radians per second. Okay, so that's the end of this unit. So if you have any questions, contact me in the normal fashion. Take care.